So hello again. This was related to a presentation I did months ago regarding the redshift and if it progresses into longer wavelengths, lower frequencies, and turns out that it does. And so I've put some new information together and we'll go over that. So I'm not going to get into much detail about redshift itself. Suffice it to say that as the universe expands, the particular frequencies of things move from visible down into red, down into infrared, down into microwave, and that's kind of where public attention of it stops. But apparently it progresses further down. And it's kind of like limbo. How low can you go? How long can the wavelength be for a photon? And how low can its energy be? Because as it moves down, the wavelength gets longer, frequency gets lower, and the energy level of the individual photon gets diminished. So over the billions of years of the universe, things are progressively to lower frequencies. I have a presumption that the continuation of the progression is just unlimited. There's no bottom to it. The photons don't just go away. They might become invisible to our instruments, but they don't go away. So how do we observe these longer wavelengths? The first problem you run into is these objects that are moving away, they may be moving away, expanding faster than their closing distance for us to receive their signal. So we might never get the signal. Not necessarily faster than light, but just fast enough that we may not have received the signal yet, and we may not receive it for some amount of time. The next thing that gets in the way is the opacity of the Earth's atmosphere, the ability for these longer wavelengths to actually make it through the Earth's atmosphere so we can observe them using radio antennas on Earth. As you get to longer wavelengths, lower frequencies, lower energies, they don't pass through the Earth's atmosphere. So you need to put your radio receiver in space. And also in space, there is all kinds of noise, natural noise that you want to make sure you're not going, oh, I heard that. And no, that's just a natural noise source. It's not really what you're looking for. And these are called Schumann Resonances. And the core of the Schumann resonance is about 7.83 hertz, not gigahertz, not megahertz, not kilohertz, hertz. Then it scales up to harmonics of that. And then what kind of an antenna do we need for receiving these very weak signals out in space? There's all kinds of antennas. There's monopoles, dipoles, parabolic dish antennas, flat panel grids. Let's start with just, a dipole, something simple, easy to pack into a rocket launch. Do we need just one antenna or do we need an array of them to create a synthetic aperture to gather more signal? Well, let's start with the dipole and then work our way up. If you think about a mobile phone, the early mobile phones had an antenna, had a big stub antenna, and then they had a telescope antenna, and they added more and more radios to your mobile phone. You have 4G, 5G, GPS, that's GNSS, Bluetooth, near field communication, RFID tags. All these things are radios in your mobile phone. Where's the antennas? Well, they do what is known as have a fractal antenna. The antenna is a small fractional length versus the wavelength you're trying to receive. And then they use a digital signal processor and amplifiers to boost the signal. So you now have a handful of antennas inside your mobile phone and no stub sticking out anywhere. We don't have to have a ginormous antenna out in space. We can build the right kind of antennas with the right electronics behind them, and you don't need, football field size antenna. But let's say you have a big antenna. How would you get that to fit inside of a rocket fairing? Well, you can make a parabolic dish that's small enough as a dish to fit inside the diameter of the upper stage of the rocket, or you can have it unfurl. You can have it open up like an umbrella. You can have it, spin sideways. Or you can have it as a flat panel where you have like origami kinds of stuff where the things just unfold and eventually become something large. And down at the bottom, you see 3 examples of this. GPS satellites have a giant parabolic fixed antenna. It's a solid dish. There's a spy satellite called a NIST satellite, and it uses radar. So it's got a radar antenna for transmitting and a radar antenna for receiving. And the sort of orangish lobe you see below the satellite, that's the transmitting antenna. And then the giant thing you see above it is the receiving antenna, because it has to be bigger to pick up the weaker signals. And that thing literally just spun itself open. And then on the right is Blue Walker 3. And that started out as something that's just a small rectangular thing. And then when it got into space, it just sort of started unfolding itself and created this football field sized antenna. So big antenna is not a problem in space. I do remember reporting this in the last presentation, but I didn't have a lot of details because I was constrained as to how much of the actual resultant report I could read because it's out of China. But now it's publicly accessible, full length of the observation research reports. They put 2 satellites into space from China, Longjiang 1 and 2, also known as DSLWP A1 and A2. And they operated on the ham radio satellite bands as Oscar 93 and Oscar 94. They put these, or attempted to put them, out into lunar orbit. So they would go out to the moon and go around the moon. And by going around the moon, there'd be a period of time where it's on the far side of the moon, and the moon, the earth, and the sun are behind it, and the moon blocks radio emissions from Earth, noise from Earth, noise from the sun, and they could look out into space. They looked in the 1 megahertz to 30 megahertz range. That's way too short a wavelength, way too high a frequency. And the bandwidth, the resolution of the receiver was only 39 kilohertz. That's kind of like a ham radio. A1, one of the 2 satellites, had issues and remained in Earth orbit. A2 actually made it to lunar orbit and operated for 437 days. So it was going around the moon. And when they got done with it, I guess when it kind of ran out of orbital correction fuel, they steered it into the far side of the moon and crashed it because they didn't want it to be debris in lunar orbit. So it had not a dipole antenna, a tripole antenna, but it was originally designed for ham radio receiving. As it was coming around the near side of the moon, ham radio operators could listen to the signals from it. So that kind of narrowed down the frequency range. Also was how strong a signal, how wide a signal it could use to communicate. After they did their observations, what they found out was, yes, there's likely signals out in space at much lower frequency ranges than microwave, but they were unable to pin them down because the satellite's receiver was not sensitive enough and the satellite's receiver was not broadband enough to receive them. Essentially, the received signal was not significantly above the noise floor of space for the receiver that they had, for the antennas that they had. That doesn't mean it doesn't exist. They detected that there's something down there, but they couldn't pull it out of the noise. So next time they do this, try it with a lower frequency, go all the way down to like 0 hertz, not megahertz, but come down into like maybe 0 hertz to 1 megahertz. And instead of having 39 kilohertz resolution, have a couple of megahertz resolution. Get some much longer wavelengths, much lower frequencies, and be able to receive a much wider signal. To make it more sensitive, instead of it just being an ambient temperature receiver, make it liquid helium cool, make it very high resolution, make it amplify considerably, and then stack the signals. So sample faster and then take multiple samples and stack them to average out the noise floor, just like amateur imaging astronomy does. They've attempted it, didn't get what they expected. Try putting up something that might actually receive what's out there or what's been postulated as being out there. But it may eventually become undetectable. If the progression does exist, we know it goes from visible to infrared to microwave, but does it continue on from there? We don't have any evidence of that, no observations for it. But if, as the China probe going around the moon pointed out, if your sensor can't detect it, it doesn't mean it's not there. It maybe means you don't have enough amplification. Your receiver's not sensitive enough. So make better, make a better receiver. If this has been happening for billions of years and the wavelengths are getting longer and longer and longer, frequencies lower and lower and lower, energies lower and lower, what is the limit of that? There's no known limit of that. And therefore, there may be lots of photons all around us that we can't detect, certainly not with our eyes, not with our microwave radio receivers, and maybe below the Earth's atmosphere, not with long wave radio receivers. So we have to get out into space with the right kind of antennas and receivers. The best place for doing that would be on the far side of the moon. But you have to come back around to the near side of the moon so you can communicate with Earth and send back what you've observed. But that's why the arrow at the bottom just goes off the right red to white. And that's just indicating we're eventually going to not have the technology to observe them. But if they are there and they're producing radiation reflection pressure, sounds dark to me. Maybe that's what the expansion of the universe is all about. So in summary, the red shift below microwave apparently continues. We've tried, listening to it longer than the microwave background, longer wavelengths. The observability of it is you can't listen to those longer wavelengths beneath the Earth's atmosphere, or they may not have arrived yet. Start by putting something out in space orbiting the moon and use the right kind of receivers to detect that it's gone even further. And you want a radio spectroscopic type analysis where you can see the shift. You know what the frequencies are of particular types of stars, point it in the direction of a star that's even farther away and see how much further the shift is to longer than microwave. And the antenna size, how many you need, all those kind of things become relevant. Start with something simpler, easier, less expensive. Ultimately, the light may be moving away fast enough that it might not catch up with Earth for a long period of time, if ever. And then we have to make sure that we have the right technology instruments. There's a thing called the photoelectric effect, which is you take in a photon, expose a material with that photon, and it produces an electrical charge, and you drain that charge away as a voltage. You amplify the voltage, and that's how you pick up the radio signal. But you have to have the right materials, because if the material you're using cannot be excited but by such a low energy photon, you won't detect anything. So make better receivers. If this has been happening for billions of years, what is the volume density of all of these non-observable photons? And if they're producing a radiation pressure because of the density of them, then maybe the thing that's pushing everything apart that is dark is actually just light pressure. But it's just a postulation. So what is spectroscopy? Redshift, cosmic microwave. The most distant galaxy is a Z of 14. So think of it as if the universe is 13.8 billion years, this is how to get to 14. Well, you can read the article. And then how to receive the radio signals of these longer wavelengths using satellites. And then what are these longer wavelengths? And then those Schumann resonances that I mentioned. And then NIST, the U.S. National Institutes of Standards and Technology, has a website that shows you the ionization energy, how much energy you need to excite the photoelectric effect, to produce the electrons that you can detect as a signal. And then what that would be for the photoelectric effect, look for the threshold frequency of whatever material you're using for your detector. And then once again, what is radiation pressure? Comments, questions?
I enjoyed it. Oh, that was good. And I think it went into more detail than what we knew in the past.
Yes,
And
that was the idea of tonight's presentation. Is I've mentioned this before, but now I had access to more details. I actually deleted a slide that was calculating the energy levels and how they shifted, and it was just a full page of math, and I thought nobody needs that.
well, I've been studying math lately. However, I don't think I would get that.
Which is why I deleted that slide. There was just too much math. I mean, it took me an hour plus to come up with all the formulas and measurements and stuff, but I went, nah.
After an hour worth of work, down the drain. Wow.
Life goes on. And if I have no more questions, then I'll stop recording. Yes. Hearing nothing.